In this lesson, we will study different types of number systems, ones that have occurred throughout history, as well as take a closer look at our own base 10 number system. So, to start with, just a couple of definitions. A number is this abstract idea, an abstraction that is used to record some number of things. And a numeral is the symbol or group of symbols that we'll use to represent this abstraction, this number. So, for example, here is an image of some sheep in a field, and if you count them, it looks like there is 21. So, in our number system, as I'm sure you're very familiar, the base 10 number system, we use 10 different symbols to represent all of our numbers. Of course, those symbols are 0, 1, 2, and then we keep going until we get up to 9. So these here, we have a total of 10 symbols, which is why we call this thing base 10. Now, in terms of counting the sheep in this field and recording it down, the way that we do it is by using place values. So like I said, it looks like there's 21 total sheep. Well, this 1 here is actually in the what we call the ones place. And this 2 here is in what we call the tens place. So this means we have 2 groups of 10, so that's 2 groups of 10. And then we have this 1 here, which is just in the ones place, meaning there's just 1 left over for a total of 21. So here's the numeral that represents the number of sheep in the field in this case. Just a little terminology. Our base 10 number system is also referred to as the Hindu-Arabic number system. This terminology pays homage to where our system came from. It originated in India, spread into the Middle East, and then eventually to the rest of the world. Now, while this is the system that we use today, throughout history, different civilizations used different number systems. So, for example, let's take a look at Babylonian numerals. This is the number system that was used by the Babylonians, and I think this was around maybe, let's say, 1500 BC in what is modern-day Iraq. But their system was not base 10, it was base 60. This means they had numerals that allowed them to count not just from 0 up to 9 before moving to a new place value, but 0 up to 59. So they actually have a specific numeral for 21, and I'll write that down here. They represented 21 like this. This is what means 21. And this all was in just the very first place value. Because they have base 60, they didn't have to move on to another place value. There was already a symbol to represent this exact amount. Another civilization that had a different number system were the Mayans. So there's also Mayan numerals. And this was circa 500 AD in Central America around the Yucatan Peninsula. Now, their number system was base 20. And that means they had 20 symbols starting at 0 going up to 19, and they went from there. Their number system was different because instead of writing numbers in a horizontal line, they'd write them vertically. So the way that they would represent 21 in this case would be 1 dot here and the 1 directly above it. And this is the same thing as saying 21. And I'll mention one more number system here used by the Romans, which is Roman numerals. The first use of these in history was circa 800 BC. And the way you could represent 21 using Roman numerals would be X, X, and I. And this here means 21. So this was just a brief overview of different number systems that have occurred throughout history. What we'll do in the rest of this lesson is take a closer look at our base 10 or Hindu-Arabic number system, and then do a couple of computations going from these number systems back into our base 10 system. To understand our base 10 number system, or really any of the other number systems that we talked about already, we have to understand what it means to be an exponent. And so here I have a definition. I'm going to let the variables b and n stand for any of these integers, 0, 1, 2, 3, and so on. We call b, this lower number here, the base, and we call n the exponent. And what this symbol means is you take the base, b, and you repeatedly multiply it to itself over and over again n times. So here, the number of times that we multiply the base is n. To bring meaning to this definition, we'll do a few computations. So let's start with this one here in example 1. What is 5, the base 5, to the power, the exponent of 2? So what is 5 squared? This means you take the base, which is 5, and you multiply it until you see a total of 2 5s. And 5 times 5 is 25. So 5 squared, or 5 to the power of 2, is 25. It's important to note that 5 squared does not mean 5 times 2, which is 10. It does not mean that. This is a new symbol for a brand new definition. It doesn't just mean multiply these two numbers together. It means take the 5, write it down 2 times, and multiply those things together. What about 3 to the 4th? What about that? 3 to the power of 4 means 3 times 3 times 3 times 3. So that is the base is 3, the exponent is 4. We write down 3 multiplied 4 times. Let's see, 3 times 3 is 9. So this is really 9 times 9. I'll put that next. And 9 times 9 is 81. Again, this does not mean 3 times 4, which is 12. In fact, it's this value here. What about 0 to the power of 3? So I'll put that over here. 0 cubed is another way you could say this. Well, the base is 0. You would write it down a total of 3 times. And 0 times 0 times 0 is actually just equal to 0. Now, how does this relate to our base 10 number system? Notice that they call it base 10. And for that reason, I'd like to compute 10 to the 1st, 2nd, 3rd, and 4th, and actually get values for what those things are equal to. So let's start with, well, what's 10 to the 1st power? This means you copy down 10 once, and you're done. Okay, so that's 10 to the 1st is just 10. Now, what is 10 squared? This is 10 times 10, and that is equal to 100. 10 cubed, the next one in our list, is 10 times 10 times 10, which is 100 times 10, which is equal to 1,000. And I have one more here, 10 to the power of 4. Again, that's 10 times 10 times 10 times 10. Well, 10 times 10 is 100, and 10 times 10 is 100. This is 100 times 100, and that is equal to 10,000. Maybe I'll put a comma here and here just to distinguish these a little bit better. So we have 10 to the 1st, 2nd, 3rd, and 4th. We had 10, 100, 1,000, and 10,000. Let's make an observation here. And this is a really good reason for using a base 10 number system. When you have 10 to the 1st, it was very easy to figure out. And 10 squared wasn't more difficult. The connection is that if you take 10 and raise it to the power of 2, you have a 1 followed by 2 zeros. Here, 10 to the 1st is a 1 followed by 1 0. Does this pattern hold true? And the answer is yes. If you look at 10 cubed, that is a 1 followed by 3 zeros. 10 to the 4th is a 1 followed by 4 zeros. So I'm going to state this as a fact. If you take 10 to some integer power n, what you get is a 1, and it's followed by n zeros. So a base of 10 is nice when doing these computations because these numbers are very easy to compute using this fact here. Before moving on, there is one last question. What is 10 to the power of 0? What is this equal to? Well, according to this fact, it should be a 1 followed by 0 zeros, meaning no zeros. And that means it's just the number 1. Notice that this works very well with our pattern. As you increase the exponents, you are increasing the number of zeros that go after 1. Here there are no zeros. Here there's 1, 2, 3, and 4. And if you go backwards, you are decreasing the number of zeros by 1. Therefore, if you want to go from 10 to the first to 10 to the 0, you'd have to drop this 0, leaving you with 1 left over. This is actually true for any base equaling 1, 2, 3, or 4, and so on. And so I'll state this as a fact as well. If you have any base, b, raised to the power of 0, this is also equal to 1, provided that your base is either 1, 2, 3, 4, and so on. So just to recap, the base 10 number system is nice because when you're computing 10 to exponents, it's very easy to determine what those numbers are equal to. Okay, now that we have a definition and an understanding of how exponents work with a base of 10, I'd like to write the number 30,475 in expanded form. This is a way of writing this number so we can actually see the powers of 10 for every single place value. Here's what I mean by that. I'll write down the number, 30,475. What are the place values for each of these digits, starting with this 5 here? Well, this 5 is in the ones place. This 7 is in the tens place. Now, why are they called this? The ones place you can think of as 10 to the power of 0, and the reason for this is 10 to the power of 0 is just equal to 1. The 7 being in the tens place means we have 10 to the power of 1. What place value is the 4 in? Well, it's in the hundreds place. And what that means is we have 10 to the power of 2. And this trend continues in our number system. This is the thousands place. So here I'll put, well, this spot is the thousands. And we call it this because we have 10 to the power of 3. And lastly, this 3 here is in the 10,000s place. And we call it that because that's 10 to the power of 4. That is a 1 followed by 4 zeros. Expanded form means we're going to take this number and we're going to write it out as a sum using these place values here. Here's what that will look like. I'm going to start with the 10,000s place. When you say 3 here, we're really saying you have 3 groups of 10,000, so 30,000. The way you could write this is as 3 times 10 to the power of 4. 10 to the power of 4 is 10,000. Multiplied by 3 is this 30,000 right here. Now, to complete this number, you have to add on all of the remaining place values. Here's the thousands place. Now, technically, we're saying there are 0 thousands in this condensed number, but you could write that like this. That's 0 times 10 to the power of 3. There are 3 10,000s, but we're going to add on 0 thousands. And we'll continue down the line. I'll now add on the 4 times 10 to the power of 2. So here in the hundreds place, we have 4, which we're really saying 400, which is 4 times 10 squared. For this 7, we will add on 7 times 10 to the first. And then for the last spot, it is going to be 5 times 10 to the power of 0. This expression that we have over here is what we call expanded form. We're expanding it out so we can actually see in each spot the digit for each place value and the corresponding power of 10 that's associated with it. Now, if you'd like, you can actually simplify this a little bit. Like, for example, here. I mean, we really don't need to put 0 times 10 to the power of 3. This all just multiplies to 0, which means we don't have to write it. And also down here, 10 to the 0 we know is equal to 1, and 1 times 5 is just 5. We could just call this whole thing here 5. Maybe a shorter way to write this would be 3 times 10 to the 4th. I really don't need to write the next one because there's really nothing there. So I'll skip over to 4 times 10 squared. I'll add on 7 times I'll just put 10 because 10 and 10 to the first are the same thing. And then lastly, I'll put plus 5. This is expanded form 2. This one I'd say is just a little bit more simplified because we're leaving out things that we really do not need. So here's how to expand out a numeral in a base 10 number system. The important thing to consider is that we have powers of 10s in these spots here. And the reason for this is because we have a base 10 number system. If you have a number system with a different base, the only difference is we won't use 10, we'll use whatever the base happens to be for that system. Let's check that out by looking at an example with the Babylonian numerals. In example 3, I'd like to write the following Babylonian numerals as Hindu Arabic numerals, meaning change them to our base 10 number system. I'll note that a V symbol represents 1, and this less than symbol is going to represent 10. So how does this work for this first numeral here? Well, in a sense, it's a lot like our number system, where they use place values. Here's the first place value, and here's the second. Here's a difference, though. They put a little space between their first and second place values. Here is a lot like their ones place value, so this spot right here. And then this is the next place value over. In the previous example, this first place value was 10 to the power of 0, which we called the ones place. And then this spot over was going to be 10 to the power of 1, which is the tens place. Since the Babylonians had a base 60 number system, the difference here is this won't be 10 to the 0 and 10 to the first. Instead, it's going to be 60 to the power of 0 and 60 to the power of 1, because this is the base for their number system. Now, in each place value, we just have to count how much stuff there is. If this symbol denotes a 1 and a 1 means we have a total of 2. So there's 2 in this place value. In this place value, there's a total of 10. If we want to expand this out to get a base 10 number, we'll do exactly what we did in the previous slide. We're going to take the digit and multiply it by the corresponding base. So that's 10 times 60 to the power of 1 instead of 10 to the power of 1. To that, we'll add on the next digit, which is 2, times 60 to the power of 0. All we need to do is simplify this number. Well, this is 10 times 60 plus 2 times 1. 10 times 60 is 600. 2 times 1 is 2. The base 10 number is 602. So this numeral here, the Babylonian numeral, is equivalent to this base 10 numeral 602. Let's try that again for this numeral here. Again, we have two different place values. For this first one, this is 60 to the 0. It's the ones place. And then here we have 60 to the power of 1, I guess you could say 60s place. What we need to do is count up in each place value how much stuff is there. Well, this is a 10 and a 1, so that is a total of 11. And here we have a 10 and a 10, which is 20 and a 1. This is 21. If we want to expand this out into a Hindu Arabic numeral, that's 21 times 60 to the power of 1. That's the amount of stuff that occupies this place value. We take the product. To that, we add on 11 times 60 to the power of 0. Okay, so if we expand this out, that's 21 times 60, and that's plus 11 times 1. And 21 times 60 plus, 11 times 1 is just 11. To multiply that out, we need to do 21 times 60. Bring down the 0. We have a 6 and a 1 and a 2. So this is 1,260 plus 11. And we add those together, we get 1,271. That is the corresponding base 10 numeral that represents these numerals here. In example 4, I'd like to write a Mayan numeral as a Hindu Arabic numeral, meaning convert one of these into something that is base 10. I'll first note that for the Mayan number system, they used a base 20 number system, although they modified theirs a little bit. So I'll say this is modified slightly. So I'll explain this in a little bit. First, I want to give you their convention for writing out their numbers. If you see a line, that's going to represent 5, and if you see dots, you can think of those as counting by 1. So to start with, they used a crescent symbol, something like this, to represent 0. But the second you have something greater than 0, like 1, they would just put 1 dot. And if you saw 2 dots, well, that's 2. And then no surprise that this is 3, and that this is equal to 4. But the second that they got past 4 and arrived at 5, okay, well, they'd use a line like this for 5. So the basis is, if you have a single dot, you can think of it as 1. The more dots you add, you're increasing by 1 up until you get to 5. So therefore, if you see this symbol here, a line and a dot, so this line means 5, and here you're saying you have 1 more than 5, and that's saying 6. If you had, let's say, a line and 4 dots, this is 9. Or for example, if you had 2 lines and a single dot, well, these 2 lines are 5 and 5, which is 10, and 1 more, which is 11. So over here, I'm going to write down a Mayan numeral, and we'll talk about how to convert that over into our base 10 number system. Now, for the Mayans, they didn't go left or right, but they wrote them increasing vertically to represent their place values. So for example, the lowest one is going to be your first place value. So maybe I'll put this symbol here. Now directly above that will be the next place value up, which I'll write a line and a dot. And then if I go up one further, that'll be the next place value up. That'll just be a horizontal line. So you can think of this as like the ones, then the next place value up, and then the place value up after that. Well, this first one here is a 5 of 5 and then 2 dots, which is 12. So next to it, I'll say, okay, here we have 12 in the very first place value. In the next place value, we have a line and a dot, and I know that's equal to 6 in the next place value up. And in this place value, we simply have a 5. Now, how do we actually take this information and expand it out to a base 10 number? I'll put that work over here. For each place value, you'll take the digit and then multiply it by the appropriate power over here. Now, this is going to work like our previous examples where we take the number 5 and multiply by an appropriate power. Then we add on 6 times an appropriate power. Then we add on 12 times an appropriate power. So the computation is going to be 5 multiplied by something plus 6 multiplied by something, then plus 12 multiplied by something. And the thing that would go here is going to be the powers of the numbers from the base. So here, this is the very first one. It's going to be 20 to the power of 0. If you want, you could just put a 1 here, but just for emphasis, I'm going to say that's 20 to the power of 0, which we know is equal to 1. Then as you increase up in place values, all we're doing is increasing the exponent by 1. So this would be 20 to the power of 1. And then if you go up one more, well, that's going to be 20 to the power of 2. Except they modified their system a little bit. They actually don't go to 20 to the power of 1. They do something a little bit different. It's actually 20 times 18. Now, this seems like a very strange and different convention, and it really breaks the pattern of what we've done before, but there is some logic behind this. If you look at 18 times 20, this is equal to 360, and that was the number of days in their calendar. So it was nice to actually kind of squeeze in this place value that matched up nicely with the number of days that they counted in a given year. So this is different. you actually don't simply just count up by 20s, powers of 20. When you get to the third one over, it's not 20 squared or 20 times 20. In fact, it's 18 times 20, which is equivalent to 360. But once we know this convention, the rest is just multiplying this number out. This is 5 times, well, 18 times 20 is 360. I don't really need the parentheses anymore. I'll just put 360. Then it's plus 6 times 20 to the first, which is 6 times 20, then plus 12 times 20 to the 0, which is 12 times 1. Okay, so 5 times 360 is 1800, and then 6 times 20 is 120, and then 12 times 1 is just 12. And if we add those three numbers together, we get 1,932. And this is the base 10 number that is represented by these numerals over here. And to end this lesson, I just wanted to address one thing that I didn't talk about with exponents earlier. I never actually said what 0 to the power of 0 is equal to. Like if you try to compute this, what should this value be? Now, I have a calculator here, and if I enter in 0 to the 0, it actually says error. And the reason for this is 0 to the 0 is not defined. There is no number that is 0 to the 0. And I'd like to briefly explain why this is the case, why you can't actually call this thing a number. We stated earlier that if you have a number b, and b is equal to 1, 2, 3, or 4, or so on, and you raise that to the power of 0, you get 1. So just to reiterate, any integer b, starting at 1, going to 2 and 3, and so on, if you raise it to the power of 0, is equal to 1. Likewise, if you take the number 0 and you raise that to the number n, where n is also equal to 1, 2, 3, 4, and so on, we can easily see that this should actually be equal to 0. So this equals 1, and this is equal to 0. What happens if you try to use this definition by putting 0 in place of b? If you do that, you get 0 to the 0 is equal to 1. Hey, maybe 0 to the 0 should be 1. Maybe that would be a fine definition. However, when you put 0 in over here, you get that 0 to the 0 is equal to 0. And the question is, well, which should it be? Should 0 to the 0 be 1? Maybe that would be our definition. Or maybe 0 to the 0 is 0. Maybe this is our definition. If this happens, where we get conflicting information from our previous definitions, in a lot of cases, it's easier to say, let's just not define it. We won't define it so 0 to the 0 is equal to 1 or 0 to the 0 is equal to 0. We'll just say it's not defined. This will not be an issue that we'll have to address often, if at all, in this class, but just in case if you were curious, if you try to do 0 to the 0, you'll actually get an error message from your calculator. And the reason is there are two conflicting ideas, and it can't be both of those things. It has to be one or the other, and we just say, well, we just won't define it at all. All right, that's everything for this lesson.